Hello all, welcome back. So in this today's session, we are going to understand how to design the clocked SR latch, right? So if you understand my previous classes, we have explained about the SR latch by using NAND gate as well as the NOR gate representation, right? So what do you mean by this one is, suppose for example, if you are considering the NAND gate representation, it is something like this, right? First we will be having the reset value, then we will be having the set value, right? So one is reset value, another one is the set value. Somehow it is connected to this one, somehow this is connected to this one. If you have feedback connected, then it is called as the sequential logic circuit. We will be getting the output, one is qn, another one is the qn bar, right? So now if you understand this one, right, so this is the basic operation of the SR latch. So the whole thing is nothing but the operation of the SR latch. Now what is the meaning of clocked SR latch? Means somehow if you connected to this circuit clock operation, then it is called as the SR latch, or we can call it as the flip-flop also, right? So what do you mean by flip-flop means? So we will be having the latch concept only. It means that we will be having the latch circuit diagram only. For along with the latch circuit diagram, we will be having the clock signal, right? What is the use of clock signal? Means based on the activation of the clock signal, so the memory element value will be taken, right? So if you don't understand, right, so we'll go back to the previous lectures so that you can understand. Now if you see that this is the latch operation or asynchronous sequential circuit. Now see that here we will be having the delay element. Once that particular time period is completed, automatically it is going to the input, right? So with whether we are giving the input value, nothing but external value or not, automatically you are taking 160 seconds is completed, the delay element is giving the value to here. So even though if you are not giving the value, it is going to be processed. It means that you are getting some improper output value. Now what is the exactly thing is that, so here if we can able to implement some control mechanism, right? That control mechanism we can as the clock signal value, right? So if this control mechanism or clock signal value equal to set to be 1 means activated, then this value will go to here, right? It means that the moment we are giving the input value, external input value, the moment if we activated this one, then only this value will go to here, right? So it means that here we have the control mechanism over the memory element, right? So that is what we called as the synchronous sequential circuit. This can be designed by using of the flip-flop operation. Simple thing is that the latch plus control mechanism, nothing but the clock, is called as the flip-flop operations. Flip means 1, flop means 0, right? So remember. So if you observe here, this is an example for the synchronous sequential circuit. It means that here we will be having the delay element or memory element. So this is controlled by the clock signal, right? So how it is controlled by the clock signal means, for the same latch, if you are adding the clock signal, then it is called as the flip-flop operation, right? So now we will try to design the basic flip-flop, right? So how we can convert this normal latch in terms of the control element for the memory element. So that is what we called as the flip-flop. In this today's section, we are going to design the basic flip-flop, right? So let me go back to my main slide. Right, now how to design the clock signal, right? So for example, here is requirement something for the exam. So I'm going to take something input like this, right? So input, I'm going to take the 2 input terminal value. Why 2 input terminal means, if you observe here, so whatever you are taking, either NAND gate or NOR gate representation, we have the 2 input terminals, right? So here we will be having the output value, right? So this input, right? So what is the possibilities? 0 0 0 1 1 0 1 1 are the possible values, right? Now if you observe here, instead of taking this value as the a value, we can consider this value as the clock value, so that we will be understand easier man. So just I'm going to replace the one of the input equal to, this is nothing but the clock. CLK means here clock is nothing but the, we can write in short form, clock, right? So now see that we have the 2 options, right? As we said in the previous slide, if you observe here, what will be happen here is, right, so when clock equal to set to be 1, that whatever the value stored in the memory will go to the input. When clock equal to 0, whatever the value you are trying to give, it means that when clock equal to 0, either it may be 1 or 0 which is stored in the memory element. So obviously it should go to 0 only. It means that it should not give any value. Any value means output should be in terms of the 0 only. Simple point to be remember is that when clock equal to 0, always output should be 0 only. Either this may be 1, input is 1 or 0, output should be always 0 only, because if clock is deactivated means output should be always 0. This point you have to remember. This is important to be understand the further concept, right? So when clock equal to 1, then whatever the value stored here, then that will be your output value, right? So this requirement should be satisfied. So based on that, we need to design some logic circuit so that can be work as the your clock signal value, right? So if you observe here, so clock means single input value, right? So either it may be possibility will be either it may be 0 or 1, right? So two possibility, right, for single input value. So for that, here I'm going to consider the when clock equal to 0. It means that what is the meaning of this one? When clock equal to 0, it means that when clock equal to absent, right? So again here I'm going to consider when clock equal to 1. So what is the meaning of clock equal to 1? So clock equal to present means output should be input should be equal to output value, means whatever the value you are trying to pass, that value should be reset to the output. But if clock equal to absent means input whatever you are trying to give, output should be always 0 only, because it should not give any output in the absence of the clock pulse. Remember that point. Now if you have the doubt why I have taken the 2 zeros once, why I have taken the 2 zeros 2 ones for the clock pulse, means if we consider one more input variable is the b, right, that is a normal input value, right? So it means that either it may be 0 or 1, right? For that reason, for two clocks, and means for the same clocks, either it may be input is 0 or 1. For again for the clock 1, the input may be either 0 or 1. So for that reason, so we have taken the when clock equal to 0 2 times. For input either it may be 0 or 1. When clock equal to 1, so what is the input value? Either it may be 0 or 1, right? So this logic you have to remember. So why we are implementing this truth table means I need to design the clock circuit, but what the clock circuit should do is when clock equal to 0, whatever the input you are giving, suppose if you are giving the input 1, output should be 0. If you are trying to pass input 0 also, output should be 0 when clock equal to 0. This is our requirement. Clock 0 means nothing should be passed, nothing means output value should be 0. Right? So when clock equal to 1 means whatever the value stored in the memory element, either it may be binary number 0 or 1, that should be passed to the output. It means that if you are giving input equal to 1, output should be 1. If you are giving input equal to 0, output equal to, it means that whatever the value are stored in the memory element, that should be passed to the circuit. Whatever the value stored in the memory element, that should be passed to the circuit. But in case of clock equal to 0, even if 1 is stored, it should not give any value. If something is stored, it should not give any value. So absence means 0, presence means the input will be equal to the output value. So based on this, we need to design the some logic circuit diagram. So if we can able to implement that logic circuit diagram, then along with the latch, we have the control mechanism, nothing but the clock signal value. So this is what we call as the flip-flop operation, right? So if you see that this title is for latch, if you are adding the clock, then this is called as the clocked SR latch, or we can call it as the directly flip-flop operation. Flip-flop operation means latch along with the clock pulse. Now what we are going to do is, for this circuit, I am going to design the extra thing, nothing but the clock signal value. To find out what is the corresponding logic circuit diagram, I am implementing this truth table operation, right? Now what is my requirement here? If you observe here, when clock equal to 0, right? So now question is that how many AND gates are required, because we have the two inputs, right, reset and set. So that reason we will consider the two AND gate representation for the representation of the clock. So one is AND gate, another one is the one more AND gate representation, right? So how many minimum number of input terminals should be there for AND gate? 2 input terminal, right? So here also 2 input terminal, right? So how many inputs we have? 2 inputs, right? One is for set, another one is for the reset, right? As we discussed in the latch, so first we need to take the R value, then S value, right? The same thing I am going to consider the R value as well as the S value, right? So now here we should have the one of the terminal should be, second terminal should be clock pulse value. So when clock equal to 1, according to input value, you will be getting the output value. When clock equal to 0, right, whatever you are trying to give the input value, so output remains 0. Means one of the terminal should be clock pulse value along with your input values, right? So along with input values, this is nothing but along with your input value, one of the terminal should be clock pulse value. If R as well as the S is my input value, then these two things will be, this one as well as this one should be clock pulse value, right? So this is one more my clock pulse value, this is another clock pulse value. But if you observe here, right, so this is also clock pulse value, this is also clock pulse value. So instead of giving the separate two clock values externally, instead of giving the two clock signals, if somehow if you connected to this one, instead of passing the two times, we can pass the value only single time representation. So for that, what I'm trying to do is I'm going to connect this one with this one, because this is also clock signal, this is also clock signal. Now what is this one we call clock signal. So instead of applying the two times, if we can able to apply only single time. Now what is this terminal value? R value. What is this terminal value? S value, right? So now what is this point we called as the clock signal. So what is this we called as the latch. So combination of the clock plus latch, what we called as the flip-flop operation, right? So this is how we are going to design the flip-flop by implementing of the clock signal value. Now still it is pending, right? So we need to connect this output to this input, this output to the input, right? So this is what we called as the simple RS, right? So flip-flop, we have the clock pulse, means this is nothing but the flip-flop, right? So now one more modification, this is also correct. Then one more modification we can do here is that, what is that modification is that, as we discussed, generally this is also correct, but when we can directly convert all the components in terms of the NAND gate or NOR gate representation, right? So reason is that those are the universal logic gates. Then one more will be delays will be very less, because the same kind of logic gates means delays will be less compared to implementation with the different type of the logic gates, right? So for that reason, what I'm going to do is I'm going to try to convert this one into this one in terms of the NAND gate representation, so that everything will be look like in terms of the NAND gate representation. So how to convert this one, right? So as I told that, so R means 0, S means 1, right? R means 0, S means 1, right? So this, if you want to write something like this, R bar, S bar means what is the meaning of this one, right? So R bar means what is the value, 0, right? So this means that 0 bar, 0 bar means 1. So what is the meaning of 1? S, right? So this is 1, correct? And the meaning of this one is that if you are converting this one into the R bar, right? So you can get the S value, right? So one more thing is that, see here, if S equal to 1, right? So what is the meaning of S bar? S bar is nothing but the R, means S means 1, 1 bar means R value equal to 0, right? 0 equal to 0, something like this. So now what I'm going to do is, actually we need to write the input terminal as the R and S, right? Now what I'm going to do means I'm going to just perform the inverse operation. So inverse operation means I'm going to take this as the R bar, I'm going to take this as the S bar, right? So here if you have taken the complement means, now what we have to do means, here we need to keep the bubble, right? So just we are keeping the bubble in order to convert in terms of the NAND gate operation. So what is the meaning of R bar? So either we can write the R bar. So what is the meaning of R bar? R equal to 0, right? R bar means 0 bar equal to 1, right? So what is the meaning of 1? Instead of 1 we can write the S, right? So here what is the S bar value means, we can write as the directly R or S bar, right? So in case of latch we are using the RS, in case of flip-flop, but if we are using the NAND gate representation here, we are using the SR. Remember, for flip-flop it should be SR, for latch it should be RS, right? So for latch it should be RS, for flip-flop it should be SR, input values. Why means this AND gate we converted into the NAND gate operation. What is the need of converting? But everything look like in terms of only NAND gate representation. For that we are trying to convert, right? So for that reason, if you are keeping the bubble here, so we are converting this R bar. So R bar can be written as the S, right? So in the next class what we will try to do is, right, so we will try to explain what is the basic operation of the SR flip-flop, then how to draw the logic circuit diagram. This is the same logic circuit diagram, then we will see the truth table operation, then finally we will see how to find out the characteristic equation for SR flip-flop. Then once finally completed, then we will try to draw the excitation table, right? Thank you.